Section: Introduction. In this section, we explore the recent advancements in machine learning, particularly focusing on how training large models on extensive datasets has become essential. We recognize that executing a single training run can demand significant data, computational power, and time, often spanning weeks or months. To enhance the success of these large-scale efforts, the machine learning community is increasingly leaning towards algorithms that not only perform well but also offer predictable outcomes as we scale up computation and data. This allows us to anticipate performance from smaller experiments without needing to conduct the larger ones. We investigate whether deep reinforcement learning (RL) can also benefit from this scaling and predictability. Our focus is on value-based methods that utilize temporal difference learning to train value functions, which have shown effectiveness in smaller settings, especially in environments with dense rewards. Unlike policy gradient and search methods, value-based RL can learn from any data and requires less sampling, making it more efficient for scenarios where interacting with the environment is costly. We analyze the scaling properties by predicting the relationships between the resources needed for training. The data requirement refers to the amount of data necessary to achieve a specific performance level, while the compute requirement indicates the number of floating point operations or gradient steps needed for the same. In RL, we can enhance performance by increasing either data or compute, which we express through a budget requirement that combines both aspects. To establish these scaling relationships, we first need to predict the optimal hyperparameter settings at different scales. We identify the learning rate, batch size, and updates to data ratio as the key hyperparameters for value-based RL. While supervised learning has a wealth of theory to guide optimal hyperparameters, value-based RL faces unique challenges, such as the non-independent and identically distributed nature of training data and shifts in objectives. We demonstrate that we can account for the unique training dynamics of value-based RL and determine the best hyperparameters by adjusting the batch size and learning rate in relation to the updates to data ratio. Our model, based on a power law, effectively predicts these dependencies. With the optimal hyperparameters, we establish that data and compute requirements change predictably based on the updates to data ratio. Furthermore, we visualize the trade-off between data and compute as a Pareto frontier, allowing us to extrapolate resource needs from low to high compute and data settings. We also define an optimal balance between data and compute, which evolves predictably with higher budgets, leading to improved performance levels. Our contributions demonstrate that the behavior of value-based deep RL methods is predictable in larger data and compute contexts. Specifically, we establish clear rules for the relationships between hyperparameters, show that data and compute requirements lie on a Pareto frontier, and predict how budget allocation between data and compute evolves for optimal performance. Our findings are relevant to algorithms like SAC, BRO, and PQL, and apply to various domains such as the DeepMind Control Suite, OpenAI Gym, and Isaac Gym, challenging the notion that value-based deep RL does not scale predictably. Section Summary. In this section, we explore the scalability and predictability of deep reinforcement learning (RL) methods, particularly value-based approaches using temporal difference learning. We establish that optimal hyperparameters and resource requirements can be predicted based on the updates to data ratio, allowing us to effectively allocate data and compute resources for improved performance in larger-scale training scenarios. Section: RL Preliminaries and Notation. In this section, we explore standard off-policy online reinforcement learning (RL), where we aim to maximize the agent's return by using a replay buffer and periodically gathering new data. We focus on value-based deep RL methods that train a Q network to reduce the temporal difference error. Here, the replay buffer holds past experiences, the target Q network helps guide learning, and we sample a batch of experiences to update our Q network using a specific learning rate. We recognize that off-policy algorithms can be very efficient with samples by fully minimizing the temporal difference error over any batch of data. This efficiency translates to making more updates to the Q network for each step in the environment, which we refer to as the updates to data ratio. However, Simply increasing this ratio can sometimes lead to poorer performance. In our study, we introduce an additional hyperparameter, the updates to data ratio, alongside the learning rate and batch size, which are commonly considered in supervised learning. We aim to answer questions about the performance of a policy, the total data needed to achieve a certain performance level, and the total computational resources required, measured in terms of floating point operations or time. To illustrate the behavior of value-based RL at scale, we pose several resource optimization questions. We treat data and compute as resources and seek to determine the minimum amount of each needed to reach a specific performance target, as well as the optimal hyperparameters for training. By analyzing empirical data from smaller runs, we can establish relationships between these hyperparameters, allowing us to optimize performance when we have larger resources available. We acknowledge that while similar questions have been explored in supervised learning, they present unique challenges in online RL due to the need for the algorithm to gather its own data, complicating the relationship between data and compute. Specifically, we investigate 3 resource optimization questions: maximizing sample efficiency, minimizing compute for a given performance, and maximizing performance within total data and compute constraints. We approach these problems by fitting empirical models to understand the minimum data and compute required for various performance targets. This enables us to maximize performance given a total budget for data and compute. Next, we will present our main findings related to these optimization questions, detailing our experiments and the scaling trends we observed. We found that applying standard scaling methods from language modeling to value-based RL necessitates a deeper understanding of how different hyperparameters interact, particularly in terms of efficiency. We will formalize these relationships through empirically derived laws and demonstrate their applicability to new scenarios. Section Summary. In this section, we explore off-policy online reinforcement learning, RL, by focusing on key hyperparameters such as the updates to data, UTD, ratio, learning rate, and batch size, while addressing resource optimization questions related to maximizing sample efficiency, minimizing compute, and maximizing performance within given data and compute budgets. We aim to derive empirical laws that predict the relationships between these hyperparameters, enabling effective resource allocation without extensive experimentation. Section: Main Scaling Results. In this section, we begin by addressing the problem of maximizing sample efficiency. Our goal is to determine the minimum amount of data needed to achieve a specific performance level, while considering a limit on computational resources. We analyze how the amount of data required relates to the UTD ratio, which reflects how many updates we can make per data point. We expect that as this ratio increases, the data needed decreases because we can extract more value from each data point. However, there is a baseline amount of data required due to the inherent difficulty of the task. We propose a power law relationship between the data needed and the UTD ratio, with a minimum data requirement and certain constants. Our empirical analysis supports this relationship, showing that we can predict the data needed for higher UTD ratios beyond our initial observations. Next, we need to express the computational requirements to reach our target performance. The total compute is determined by the number of gradient steps taken multiplied by the model size. We treat the model size as a constant, allowing us to express compute as a function of the UTD ratio. We note that the compute relationship is more complex than a simple power law, as it involves a combination of 2 power laws. Both the data and compute requirements are influenced by the UTD ratio, enabling us to define a trade-off between the two. We visualize this trade-off as a curve, where moving left increases data efficiency at the cost of compute, and moving right does the opposite. Interestingly, there is a point beyond which increasing the UTD ratio does not improve compute efficiency. To solve for maximum data efficiency, we identify the largest UTD ratio that meets our compute constraints and use it to estimate the data needed. Conversely, for maximum compute efficiency, we find the smallest UTD ratio that satisfies the data constraints. Finally, we tackle the problem of maximizing performance within a given budget for data and compute. We consider a linear budget function and use our estimated Pareto frontier to identify an optimal UTD value that maximizes performance while staying within budget. We observe a power law relationship between the optimal UTD value and the budget, which allows us to predict good UTD values for larger budgets based on our low-budget experiments. This concludes our main findings. Section Summary. In this section, we analyze the relationship between the amount of data and compute required to achieve target performance, revealing a power law dependency on the UTD ratio, sigma. We establish a trade-off between data and compute efficiency, allowing us to predict optimal resource allocations for maximizing performance within given budgets. Section: Fitting relationships between. In this section, we describe how we estimate effective values for the hyperparameters, batch size and learning rate, based on the UTD ratio, which is the only variable present in many of the scaling relationships we discussed earlier. We recognize that the behavior of TD learning differs from supervised learning, where the UTD ratio does not apply. To explore the connections between batch size, learning rate, and the UTD ratio, we conducted a thorough grid search. Initially, we tried to use the common approach from supervised learning to explain the relationship between the optimal batch size and learning rate that yield the best data efficiency. We found that when the batch size is below a certain threshold, these two parameters tend to be inversely related. However, our findings showed that without considering the UTD ratio, the best batch size and learning rate had a weak correlation. Additionally, the critical batch size did not align with the empirically best batch size. Surprisingly, we discovered a strong correlation between both the optimal batch size and learning rate with the UTD ratio. Since these optimal values showed almost no correlation with each other, we decided to model them independently as functions of the UTD ratio. We explain the relationships between the optimal batch size and the UTD ratio, as well as the optimal learning rate and the UTD ratio. This understanding allows us to predict suitable values for both parameters effectively. For the optimal batch size, we propose a power law relationship with the UTD ratio, which we validate through empirical evidence. We believe that larger batch sizes can lead to overfitting because they result in repetitive training on the same data. A low training loss on the data in the buffer does not guarantee good performance for the learning agent, which can lead to poor test results. To mitigate overfitting associated with a high UTD value, we suggest reducing the batch size so that each sample is seen fewer times during training. Our empirical analysis supports the idea that a smaller batch size reduces overfitting across various tasks, indicating an inverse relationship between the optimal batch size and the UTD value. Next, we examine the relationship between the learning rate and the UTD ratio. We note that a high UTD value often results in poorer performance due to both overfitting and plasticity loss, which refers to the value network's struggle to fit TD targets later in training. Previous research indicates that plasticity loss is linked to the number of gradient steps taken and that larger parameter norms in the Q network suggest plasticity loss. We hypothesize that a higher learning rate leads to larger updates against the same TD target, making it harder to fit subsequent targets. Our observations confirm that the parameter norm increases with a high learning rate. Therefore, we propose that the optimal learning rate should scale inversely with the UTD value. Our empirical findings support this hypothesis, and we model this relationship, noting that both the optimal batch size and learning rate follow a power law in relation to the UTD ratio. Section Summary. In this section, we describe our method for estimating the hyperparameters batch size B and learning rate eta as functions of the UTD ratio sigma, revealing that both B** and eta** exhibit strong correlations with sigma while showing weak correlation with each other. We propose that B** follows an inverse power law relationship with sigma, while eta** scales inversely with sigma, both of which we empirically validate. Section: Empirical workflow for obtaining fits. In this section, we outline our workflow for estimating empirical fits after addressing specific problems. We provide more details in the implementation section and the appendix. Our workflow can also be adapted for scaling law studies with other value-based algorithms. We begin by evaluating budget extrapolation, where we present results across various environments. We estimate several Pareto frontiers for points with equal budget changes and perform a specific fit while excluding the two largest budgets. The quality of our fit for these extrapolated budgets is illustrated in the figure. Next, we evaluate Pareto frontier extrapolation using data from OpenAI Gym. We fit a data efficiency equation while excluding either the two largest data requirement values or the two largest compute requirement values. The fit quality for these extrapolated values is also shown in the figure. For hyperparameter fit extrapolation, we again use OpenAI Gym data. We plot the data efficiency fit based on our identified dependencies and extrapolate to a smaller value. We compare this with the typical approach of tuning hyperparameters for a single setting, showing that our method improves results for other values, especially for larger settings. This highlights the importance of considering hyperparameter dependencies. In discussing related work, we note that previous studies have focused on scaling laws in supervised learning, primarily predicting the impact of model size and training data on validation loss. While some extensions exist for language models, little research has been done on scaling laws in reinforcement learning, RL. We are the first to explore off-policy value-based RL methods trained through temporal difference learning, revealing distinct training dynamics and a different scaling law form compared to supervised and on-policy methods. We also address methods for large-scale deep RL, noting that naive scaling can degrade performance. Our work utilizes scaled network architectures and focuses on value-based off-policy RL algorithms, contrasting with prior studies that emphasize on-policy methods. In our discussion, we demonstrate that value-based deep RL algorithms scale predictably and establish relationships between hyperparameters, data, and compute requirements. Although our models are based on small-scale runs, they reliably extrapolate to larger scales. However, we acknowledge open questions regarding the theoretical grounding of power law models and the need to explore additional hyperparameters and trade-offs. Future work will aim to verify our findings with larger models and tasks, analyze the effects of modern architectures, and expand the range of compute scales studied. Our research is just the beginning of understanding scaling laws for value-based RL methods, with the potential to enhance our knowledge and guide future innovations in the field.